Hello students, welcome to the lecture of structure of atom. Till now we have studied about the wave nature of electromagnetic radiation and we had started the particle nature with Planck's quantum theory. With Planck's quantum theory we had learned the formula E equal to h nu and we were discussing photoelectric effect. So, next we will study more about the particle nature. So, we will start again with the photoelectric effect. So, Planck's quantum theory gave this formula that E equal to h nu, where E is the energy of radiation that is energy of radiation absorbed or emitted, and nu is the frequency of the radiation. And h is known as the Planck's constant, and it has a value of 6.626 into 10 to the power minus 34 joule second. So, this is the Planck's equation. From Planck's equation we can easily derive that frequency nu equal to E by h, and the Planck's constant stated that the atoms or molecules emit or absorb energy in discrete amounts, that is discrete quantities. Atoms or molecules absorb or emit energy in discrete quantity. Then we have started the photoelectric effect. What was the photoelectric effect? Photoelectric effect stated that when electromagnetic radiation, when a radiation strikes on a metal surface, electrons are ejected. Basically, this was the phenomenon that was observed and it was called the photoelectric effect. Now, some metals that were performed by this experiment, which H. Haas had performed an experiment inside a vacuum chamber with a metal plate and a detector connected with a battery. So, light beam was incident on this metal plate. So, this is the vacuum chamber, this is the metal plate, and this is the detector. Okay, so when the light beam was incident on the metal plate, electrons were ejected from it and it was detected with the help of this detector. So, the metals that were observed to show this photoelectric effect were potassium, rubidium, cesium, etc. Other metals are also possible. Okay. Now, photoelectric effect had some postulates. It stated that there is no time lag between the striking of light beam and ejection of electrons. And number of electrons ejected is proportional to the intensity of light. And for each metal, there is a minimum value of energy required to eject an electron. Okay, so these factors can be explained as when the light beam strikes on a metal surface, the electrons will be ejected instantly. That is, there will be no time gap between the incidence of the radiation and ejection of electrons. Electrons will be ejected from the metal plate as soon as the light beam strikes on it. And the number of electrons that is ejected is proportional to the intensity of the light. That is, higher the intensity of the incident light, higher will be the number of electrons ejected from the metal surface. And thirdly, every kind of light beam will not be able to eject electrons from a metal surface. If you take any random metal and you just project a light beam on it, ejection of electrons will not occur, because for ejection of electrons a minimum amount of energy is required, because what we know that in an atom electrons are held by the force of attraction of the nucleus. So when a light beam strikes on the atom, the energy of the light beam should overcome the energy of this attraction between the nucleus and an electron. So when the energy is able to overcome this, then only ejection of electrons will occur. So the minimum energy which is required to eject an electron from a metal surface is known as work function. And since we know that energy is directly proportional to frequency of the radiation, so the minimum frequency of radiation which is required is known as threshold frequency. And this work function or the threshold frequency are different for different metals. So, work function, it is written as this. Work function is defined as the minimum amount of energy of the incident radiation or the incident light required to eject an electron from a metal surface. This is called the work function, and we know that energy is equal to h nu, that is energy is proportional to frequency. So we can write that W naught equal to h nu naught, suppose. Okay, so h is the Planck's constant, this is and these have a constant value, and so W naught is actually proportional to nu naught. So this is called the threshold frequency. If work function is the minimum amount of energy that is required, so nu naught will be the minimum frequency that is required to eject an electron. So this is known as threshold frequency. Minimum frequency of the incident radiation required to eject an electron. Okay, now if nu naught is the minimum frequency, we know that frequency is inversely proportional to wavelength. So what will be the corresponding wavelength to nu naught? If we write it as lambda naught, then this will not be minimum wavelength, this will be maximum wavelength. Okay. Now the results of the photoelectric effect was not explained by classical mechanics or classical physics. Okay. Photoelectric effect was not explained by classical physics. Also, it was earlier it was believed that the number of electrons ejected was proportional to brightness, but this was wrong. Number of electrons is not always proportional to the brightness of the light, because it was observed that, for example, a very bright red light, okay, is not able to eject electrons. But a very weak green light is able to show photoelectric effect. Why? Because we know that frequency of red light is lower than the frequency of green light. Therefore, energy of red light will be less than energy of green light. So this depends on the energy and not on the brightness. So this concept was false. So energy is the main factor. Now a certain radiation is incident on the metal surface. The radiation has certain energy. Now the minimum energy required is called the work function. But what if the radiation that is incident on the metal surface has an energy higher than the work function? Then what will happen to the excess energy? Work function, the amount of work function is required to eject an electron. But the excess energy that is present in the radiation will be used for the kinetic energy of the electrons. It will be converted to the kinetic energy. So the total energy of the radiation has two components. It can be considered to have two components. One is the work function and another is the kinetic energy. So if total energy is E, then it can have two components. One is the work function and one is the kinetic energy. So E equal to W naught plus KE. Now E is H nu equals to work function is H nu naught, where nu naught is the threshold frequency, and kinetic energy is half mv square, where m is the mass of electron and v is the velocity of electron. Okay, this equation was given by Einstein. So Albert Einstein received Nobel Prize in Physics in 1921 for photoelectric effect. Okay, so according to Einstein, light is made up of tiny particles called photons. Each photon has an energy of h nu. So this amount of energy is called each quantum of energy, and he gave this formula that total energy is the summation of work function and kinetic energy. So next we will study further into this topic. Thank you.